so good. Sorry for delaying the course.
No, it's no problem. I had some problems with this thing, which decided not to work with that camera. But now I am recording it with my own computer when I plugged that camera in my laptop, so it should be okay. There is always someone who plugs out the cables and does not pull them back. And one of those cables is working, one of them is not, one of them is working only after a clean restart. So I will just be bringing my own laptop and doing the recording from that and showing you the slides from this one. Good. So sorry for the delay, and let's just start for today. Well, I have taken a look at the poll regarding the class change. There doesn't seem to be a solution, so we'll just have to stick with this one. That's okay, right?
Yeah.
And the ones this evening, which you will have at the end of a long day. So hopefully we'll just manage.
I think we have accepted our fate.
Okay.
But thank you for taking the time to try to fit us.
It's no worries. For me, the evening it's okay, but also I would like to go home a little earlier, right? But yeah, 7:30 is not that bad.
Yeah.
When I was a student, I had class at one point up to 8:30, and that was
that's horrible.
right. But it was a good class in statistical simulations. I liked that, so that was good. So. Last time we were talking about random vectors. We were talking about how to interpret their expectation as a vector of expectations, how to interpret the matrix of variances and covariances as well, the variant or covariance matrix, and how to deal with them when we are taking a vector, then multiplying it with a matrix or with another vector, basically making some linear combinations on that, and how the matrix behaves, how we can compute the variance of a transformed random vector, and so on and so on. Now, at the end, we have defined the multidimensional normal distribution as the extension of a one-dimensional distribution. You remember the one-dimensional normal distribution or Gaussian distribution just has the density looking like this, which is a function in the form of a bell curve, useful when modeling things which, well, arise in the nature, well, the height of people, the length of fish, and so on and so on. And then we have generalized this to working with multidimensional normal distribution, which is defined in two ways equivalently. Either we say that a random vector is multidimensionally normally distributed if, when we multiply it by another vector, we get a one-dimensional normal distribution, or we define it as such a vector which has a joint density looking like this, which is basically a multidimensional extension of the one-dimensional density. And we have seen that the multidimensional normal distribution has a couple of nifty properties. We have seen that the density function looks also like a bell curve, but raised above a plane. And if we cut it in any of the dimensions, we again get a bell curve, so a normal distribution. Now, we have seen at the end that if we take a linear transformation of a normal distribution, we get, again, a normal distribution. And so if we add up two normally distributed variables and so on and so on. And we have seen that normally distributed variables are independent if and only if they are non-correlated. So for general random variables, if random variables are independent, then they are non-correlated. But it does not need to hold reversely, but for a multidimensional normal distribution, this holds also in reverse. So if the covariance or correlation between two random variables is 0, and we know that they are normally distributed, then it also means that they are independent. So knowing a value of one of them does not influence the other in any way. This actually means that the matrix of the variances, well, the variance matrix is diagonal. So the covariance is equal to 0. And we have seen how this can be proven. Now, to continue with this, it can be proven quite simply that if we have 2, 3, 4 more randomly distributed variables which are independent and add them up, the result again has a normal distribution. Okay, so let's just say theorem. If we let x1 up to xn be independent, having the distribution n, let's say mu I sigma I squared, the normal distribution, then x1 plus x2 up to plus xn has the normal distribution where the expectation is just the sum of the original expectations mu, and the variance is just the sum of the original variances. Now this is quite useful when we are, for example, assuming that people have their weight normally distributed and the weight of individual people is independent, and we take 10 people and put them in an elevator. And we want to measure how heavy they are all together. So we have person 1 plus person 2 plus person 3 up to plus person 10. And then we know that the weight of them all together is normally distributed with the corresponding parameters. And from this, we can find probabilities that the weight of them all together will be, for example, larger than the allowed capacity of the elevator, and so on and so on. If we know how this random variable, the sum of the original ones, behaves, we know that it's normally distributed and has this and this parameters, then we can make the other statements about it. Proving this is quite simple. We go from the first definition of the normal distribution. Now, we know that if we have a multidimensional normal distribution and apply a vector on it, then it again has a normal distribution. So then we need just to think about what is a sum, x1 up to xn, x1 plus x2 plus xn. Now this is just taking a vector x1, x2, x3 up to xn and multiply it with a vector of constant 1, 1, 1, 1, 1. And then we know from the basic definition of the normal distribution that it is normally distributed. Yeah. If we just take that the sum as 1, 1, 1 up to 1 times the vector x1 up to xn, then we know, and we denote this as the vector c transpose, then ct times this vector x is normally distributed from the definition of the multidimensional normal distribution. And the parameters are then the sums of, well, the expectation is the sum of the expectations, because if we take the vector mu1 up to mun, multiply it by 1, 1, 1, 1, 1, we get just the sum of the mu's. And if we take the variance matrix and we assume that they are independent, then it is diagonal, and multiplying it multiplying it from both sides by a vector 1, 1, 1, we get just the sum of the variances. Yeah? And CT times mu1 up to mu n is just the sum of mu's, mu1 plus mu n, and CT times sigma 1 square up to sigma 2 square times C, which is, well, the variance. If we multiply a vector by a different vector in the variance matrix, it goes here and there, we'll just get that this is the sum of the variances. Okay, so a sum of independent normally distributed variables is always normally distributed. Make sense? Good. Now, another quite interesting property, or a concept maybe, better naming it, is that we can find the so-called principal components of the normal distribution. If we take a look at the density, how it looks like, here, we see that the density represents a bell curve, and it represents also the relation, the proportionality between the variables x and y in the way where it is stretched, whether be it more like this or more like this. And there is a way how to find major components inside of the relation of the two variables, and how to find lateral components. Basically, how to break down the behavior of x and y into a major direction and a minor direction. If you take a look here at this graph, this hill, then you see that there is a major direction of the relation between x and y, and here is a lateral direction. It can be proven that using the matrix calculus and what we know about eigenvalues and eigenvectors, I think you remember at least bits about those terms, we can separate the directions inside the real plane into lateral, basically independent or orthogonal parts. Now, you can imagine if you would be, for example, studying the dependence or the relation between height and weight of people, and you would take a bunch of people, measure their height and weight, you would get a graph of the individual measurements looking like this. There is a distinct proportional trend like that between height and weight. Of course, people grow to be some amount of centimeters tall, and they are linearly or proportionally that heavy. This is a basic trend. The taller a person is, the heavier he is. But there are also lateral trends to this, which are not included in the immediate relation between height and weight. Now, you can imagine if you would be, for example, comparing other way around, if you would be comparing the heights of fathers and the heights of their sons when they grew up to be adults, you would get a similar graph. You would see that taller fathers tend to have taller sons, shorter fathers tend to have shorter sons, but there is also not a direct line in there, but there are also some other influences. The height of the mother, other genetic predispositions, and so on. The same way with the height and weight. Some part of how heavy you are is predetermined how actually tall you are, and then there are other influences, be it where you are living, be it some other genetic predispositions other than the height, basically some lateral elements. And the so-called principal components analysis allows us to identify the major directions of the dependents and their orthogonal parts. This allows us, when we are, for example, modeling the dependence of something on multiple random variables, this allows us to reduce the dimensionality of the problem and just take the ones which are influencing it the most and disregard the others. This is a concept then used in machine learning if you focus on that. Now, how to do that? Let's see. This concept is called the principal components analysis, or PCA. Now, let the random vector x be normally distributed with vector of expectations mu and variant matrix sigma. Then take a look at the matrix and find its eigenvalues. Lambda 1, lambda 2, and so on up to lambda n v. Eigenvalues of the variance matrix and v1 up to vn be the corresponding eigenvectors. And let them be normalized so that they have a length of 1. Then the variables y1, which is v1 times x, y2, y3 up to yn, which is vn times x. Then such variables are independent and have a normal distribution with expectation corresponding to the corresponding eigenvector times the vector of expectations, and have the variance corresponding to the appropriate eigenvalue. Now, you recall what are the eigenvectors and eigenvalues of a matrix?
Yeah.
Those are such that if you take the matrix, multiply it with the vector, it is just the same as the vector, but multiplied by some factor of lambda. Okay, and well, how to find them? You know how to do that?
Yeah, it was determinant of A minus lambda I.
Now, if this needs to be equal, then it can be equal also if you multiply this by the identity matrix. So lambda times the identity matrix times v. If you subtract lambda times I times v, you will get that sigma v minus lambda identity matrix v has to be equal to 0 vector. Then you take the vector v and just out-multiply it So you get that sigma minus lambda times I times V has to be equal 0. No, V is actually a vector. Okay. And if you have a matrix multiplied by a vector, which is, well, a non-zero vector, and get a 0, this means that this matrix needs to, well, the corresponding set of equations, of linear equations, needs to have a solution. This means that this matrix needs to be singular and how to find where a matrix is singular, exactly as you said, the determinant of that matrix needs to be equal to 0. So this is equivalent with sigma minus lambda I, the determinant of this being equal to 0. Now to prove that this actually works, that the variables which we take as the eigenvectors times the original vector. Oh, maybe close this up, right? Come on. Yeah. This goes back to what we know from linear algebra, that if we take eigenvectors corresponding to a matrix, we find that they are orthogonal to each other. Okay? They form actually an orthogonal basis, and if we normalize them, we get an orthonormal basis. And this actually means that if we take the matrix, or the variance matrix of that normal distribution, then and multiplied by each of the vectors, we get that there is actually lambda times V. If we organize the vectors in a matrix, we get a matrix equation that sigma times the matrix of the eigenvectors, when put into columns, is actually the eigenvectors times a diagonal matrix of eigenvalues. And if we multiply this equation from the left by B, we'll get that B sigma times B transposed is B times B transposed, and because the eigenvectors are orthogonal and even orthonormal, then B times B transpose, so the matrix of the eigenvectors in rows times the matrix of the eigenvectors in columns gets us an identity matrix. And an identity matrix times a diagonal matrix of lambdas gets us the diagonal matrix of lambdas. And this is actually the variance matrix of the random vector y1 up to yn, because if we take a vector which is a matrix times a normally distributed vector, we get again a normally distributed vector, and its parameters are determined by the multiplying matrix. If we multiply by the matrix of eigenvectors the vector of expectations, we get transformed expectations, and if we multiply the variance matrix from the left and from the right, we get a diagonal matrix. So actually, yes, from what we know from basic linear algebra, we get that these transformed random normal parts of the vector are actually independent. Now, knowing how to prove this is, well, just an interesting thing which you can go through, but knowing that you can take parts, well, of a random vector and break them down into principal and orthogonal mutually independent parts, one of them containing the most of the information and the other containing the lateral influences, the less important influences, is actually quite handy. Most often when you are in the setting of machine learning. Does it make sense so far? Okay, now let's take a look at an exercise. Let me see here. 2.7. Suppose we have a normally distributed vector x1, x2, which is x1, x2, have the multidimensional normal distribution with the vector of expectations being 2 and 0, and the variance matrix being 5, 3, 3, 5. And first we want to find the joint density. So that we can write it analytically, so that we can then maybe plot it if we like. If we had a three-dimensional plotting machine in our computer. Okay. Let's take a look. Oh, sorry. Yeah. If we take a look back at the definition, then we see that the joint density, well, at point x is 1 over 2 pi to the power of n½ times the determinant of the variance matrix to the power of 1½ times e to the power of minus 1½ x minus mu transpose sigma inverse x minus mu. Okay, now the vector x has just two parts, x1 and x2. That's good. So we don't need to dwell into too many equations later. Let's first, oh, n is 2, that's clear, good. Now, if we go from left to the right, then we need the determinant. Now, this is a matrix 2 by 2, so we have a determinant of the matrix 5, 3, 3, 5. Good. How do we find the determinant of such a matrix?
5 times.
Yeah, 5 by 5 minus 3 by 3, like A, B, C. D, the determinant is AD minus BC. So we have 5 times 5 minus 3 times 3, so 25 minus 9, which is 16. Good. So this is what we would be inserting in here. That's good. Now then, x minus mu is actually a vector like x1 minus mu1, x2 minus mu2. And if we take a look, that's just x1 minus 2 and x2 minus 0. This is what we would be inserting then in here. And then we need the inverse of the matrix. Now, how do we find an inverse of a 2 by 2 matrix?
We can just
Cross, yeah.
Now, first of the possibilities is go, well,
calculator.
yes. Now, if we take the two parts, sigma and identity, then do the Gaussian elimination to get identity and sigma inverse. That's possible. In a couple of steps we would get that. Another possibility, if we have the matrix A, B, C, D, then the inverse of A, B, C, D is actually 1 over the determinant times, and now D, A minus B minus C. Okay, that's a rule named after someone which I cannot remember now. So here we take 1 over the determinant, that's 16, good. And then we take, well, 5, 5, so that stays 5 and minus minus gets us minus 3, minus 3. So that's the matrix. So we take this part, multiply it with this part, and then again with this part. So let's take a look at the exponent. So x minus mu transpose sigma inverse x minus mu gets us x minus x1 minus 2 x2, and the matrix 1 over 16 5 minus 3 minus 3 5 times x1 minus 2 x2. We just out multiply the 1 over 16, and what we have next is x1 minus x2 times 5. x1 minus 2 times 5 minus 3 times x2. That's the first part. Then we have 5 times x1. Sorry. x1 minus 2 times minus 3 plus 5 times x2. We multiply it with this x1 minus 2 x2. So that's a two-dimensional vector times two-dimensional vector producing a scalar. So we get 1 over 16 times, and now x1 minus 2 times 5 times x1 minus 2, so basically 5 times x1 minus 2 squared. Then we get minus 3 times x2, x1 minus 2. Then we have minus 3 times x1 minus 2, x2. And then we have plus 5 times x2 times x2. So x2 squared. And these two inner terms, these two parts are the same, right? So we have just minus 6 times this. And then if we insert this into the formula for the density, we get that it is just 1 over 2 pi to the power of 2 over 2, which is 1, right? Times the determinant to the power of 1/2, so basically square root of 16, which is 4, times e to the power of minus 1/2, times 1 over 16 times, and now 5 times x1 minus 2 square minus 6 times x1 minus 2 times x2 plus 5 times x squared. So this is the formula for the two-dimensional density of this random vector. If you would have a software which can plot three-dimensional functions over two-dimensional planes, by inserting this functional term in that, you would get a similar picture as we had on the picture before. Does it make sense? I have just found out device settings. Ah, that's better. So for posterity, now it is flipped in the good way. So that was part A of this problem. Part 2 is finding the principal components of that vector. So B. So basically such vectors which are linear transforms of X and are independent. Okay, so for this we need to find the eigenvectors, and for that we need to find the eigenvalues. Okay, so let's take a look. So find eigenvalues of sigma. Let's take a look at the determinant of sigma minus lambda times I is determinant of, well, 5, 3, 3, 5 minus lambda times 1001. We just mean subtracting lambda from the diagonal, right? So 5 minus lambda, 3, 3, 5 minus lambda. So we get 5 minus lambda squared minus 3 squared. So we get 5 squared minus 2 times 5 times lambda plus lambda squared minus 9. So this is 25, this is 10 lambda. So we have lambda squared minus 10 lambda, and then 25 minus 16 is 16. And this needs to be equal to 0. Okay, so that's basically a quadratic equation, right? How do we solve quadratic equations?
It's called general formula minus b plus less square root.
Yeah, of the discriminant. Okay, we know that. Let's take a look. Lambda 1, 2 is, well, minus b plus minus square root of b squared minus 4ac over 2a, right? So, minus b, that's 10. Good. Plus minus square root of b squared, that's 100. Minus 4 times a, that's 1, fortunately. times 16 over 2 times 1. So 10 times plus minus square root of. Now 100 minus 4 times 16, that's 64. 100 minus 64 is 36. So if we take the square root of 36, we get that it is 6 over 2. So that's basically 5 plus minus 3. So we get that lambda 1, the first eigenvalue, is 8, and lambda 2, the second eigenvalue, is 2. Okay?
So these rules are called algebraic something. There was geometric and algebraic for lambda, right?
Those are just the algebraic roots, right? All.
There was something near algebraic and geometric, and we were comparing them.
Yeah, I know now. I can't remember.
Yeah, me too.
Maybe spectrum or something similar. I'm sorry, don't know exactly. It's been a while that I've been teaching linear algebra here. Good, so we have the eigenvalues. So we need to find the eigenvectors and see where does this lead us. Okay, so for lambda 1 being equal to 8, finding the eigenvector means basically solving an equation with the matrix looking like this. Where, well, sigma times V1 is equal to lambda times V1. So this is equivalent with sigma minus lambda 1I times V1 being 0. So this basically means solving the equation where we have, well, 5 minus 8 and 3, 3, 5 minus 8. Okay, find a solution of system of equations with this matrix. Okay, 5 minus 8 is minus 3, 3, 3, minus 3. And so if we have a matrix and want to find a solution of system of equations with these coefficients, we use the Gaussian elimination, right? So we can, what we can do? There are 3 operations of the Gaussian elimination, right? One of them is switching rows, second of them is multiplying rows by scalars, non-zero, and third of them is adding vectors one to another. So what we can do is add the first one to the second one and get minus 3, 3, 0, 0. And then we can multiply the first one by, well, minus third, let's say, and we'll get the matrix having minus 1, 1, 0, 0. Okay.
So we have now 2 solutions, 2 vector space.
Now here, there are actually infinitely many solutions to that, but we just pick one, and pick one which we then be quite easy to normalize. Now, if we have a matrix representing linear equations with these coefficients, what would be vector solving such an equation, such a system? For example. Sorry?
1, 1.
Yeah, 1, 1. Yeah, the solution is, for example, let's take V1 with a 0 here, or with a curl here, because it's not the one which we are actually needing right now. What we need is its normalized version. Okay? So we need to take this vector and divide it by its length. What is the length of this vector?
Square roots of 2.
Square root of 2, right? So basically that's square root of 1 square plus 1 square, so square root of 2. And the normalized vector v1 is basically 1 over the length of v1 curl times v1, which is basically 1 over square root of 2 times 1, 1. So, yeah. 1 over square root of 2 times 1, 1. Good. And if we take this vector, transpose it, multiply it by the original, so we get y1, which is, well, v1 transpose times x. So we get 1 over square root of 2 times 1, 1, x1, x2. Basically, x1 plus x2 over square root of 2. So that's the first principal component. We add x1 and x2 and get divided by square root of 2, and we get the first direction. Okay? And let's see how this works for the other one, where lambda 2 is equal to 2, right? So we need to solve 5 minus 2, 3, 3, 5 minus 2. So we'll get 3, 3, 3, 3. Let's, well, subtract the first from the second. So we'll get 3, 3, 0, 0. Multiply the first by 1/3. We'll get 1, 1, 0, 0. And what would be the solution to that?
1 minus 1.
For example, yeah. And the length of this vector being just 1 square plus minus 1 square root of this, which is a square root of 2, again, so we get v2 is just 1 over square root of 2 times 1 minus 1. And the second principal component, y2, is, well, v2 times x, which is 1 over square root of 2, 1 minus 1 times x1, x2, giving us basically x1 minus x2 over square root of 2. Okay, so we have y1 and y2, which are independent on each other. They are orthogonal to each other, and they represent the main direction of, well, the hill curve and an orthogonal direction of the hill curve. Okay? Now, if we would scale them by their standard deviation, we would get the vectors corresponding to the actual sizes of well, how the hill is stretched. So we would get, let's say, v1 being square root of lambda 1 times v1, which is square root of 8 times square root of 8 times 1 over square root of 2 times 1, 1, which gets us, well, 2, 2, and v2 being square root of lambda 2 times v2, which is square root of 2 times 1 over square root of 2, 1, minus 1, giving us 1. Minus 1. Okay, so those are the principal components. If we take a look at the hill curve, then we see that this is the major component, x1 plus x2 multiplied by length, and here the lateral x1 minus x2, again scaled their length.
So V1 is major and V2 is lateral.
Yes, yes, yes. And this has to do with the order of the eigenvalues. We have taken the eigenvalues lambda 1 to be the larger one, lambda 2 being the smaller one. And this, again, by the knowledge of how linear algebra works, gets us that V1 corresponds to the major direction and V2 to the lateral. Okay? Now, if you take a look at xy, you immediately see that they are somehow related. There is some direct proportionality between them. That's good. But if we take a look at y1 and y2, basically scaled by v1 and v2, well, multiplied by v1 and v2, those two basically take this picture and rotate it like this, and then there is no correlation. It just rotates the axes. Okay? We take a look at different examples from the lecture. There we see a different vector with a different matrix. If we take a computer, find the eigenvalues and eigenvectors, you'll get the results. And yeah, for example, this means rotating such a hill into axes which are then this and that way, looking like this. Okay? Good. Does it make sense? You can know how to find those, and in other subjects you will learn how to use those. Okay? Or in real life, if you will do something related with machine learning or data processing, you might encounter the principal component analysis in one way or another, and then you will be prepared to how to deal with it. And you can learn about the background back in the slides, and it has to do that they are normally distributed, and basically the hill curve can be rotated so that we will get lateral orthogonal independent variables. Okay?
Sir, I have a doubt. How we got that V1 as a 1, 1?
Okay, this is the solution of the set of equations represented by this matrix. So we're basically searching for such a vector which, if we multiply this matrix by the vector,
Okay, so
gets us 0,
Okay.
right? And we have just chosen 1, 1 because it's the simplest one. You multiply it here, get -1 plus 1, yielding a 1. Okay? We could choose a different one. That would be also possible, -1, -1. Then the direction would just point in the other direction, but they will still be orthogonal to each other. Okay?
Yes.
Any other questions to that? Good. So with this part, we close the chapter corresponding to random vectors. So basically, you know how the random vectors can be represented with their vector of expectations, how to deal with the variance matrix, and so on, how the normal distribution behaves. Now, this week we start a completely new topic, one of the major parts of the course. It relates to the first quiz and the first homework, namely the chapter concerning entropy and coding. Now, you might have heard at times in other subjects or just read in newspapers or scientific key articles that the entropy is a measure of chaos, measure of uncertainty. We will take a look at the entropy from the framework of information theory, and we will will mostly be using and trying to quantify the uncertainty and randomness in texts and how to use this to encode the texts efficiently. One of the applications. So let's take a look. Many mathematicians before and statisticians, physicists use the measure of uncertainty in a given system in one way or another. As entropy, we understand the chaos, the number of, some measure of disorder in a system. It has been used in thermodynamics, in statistical physics, and we will be using it in the context of information theory. Now, the field of information theory is also quite broad, and we'll just be taking a look at one part of them. And you can think of the entropy as the measure of questions needed to get answers. If you have a system which is well ordered, then you just need quite a few questions to get to what you need. If you have a system which is in a real disorder, then you need more questions to get to the answer, what you need. Now, the entropy in the information theory context was introduced by Claude Shannon, and basically von Neumann told him that the new quantity which he defined to measure chaos in a system, in a information system, can be called entropy because, well, other people are calling chaos entropy, and also that the entropy as itself, as the term, is so untangible that if he starts talking about it, nobody knows what it is, and he's always gonna win an argument. So yes, it took off. Now that's the primary reference book, Elements of Information Theory by And Thomas, you can refer to it. I think it's available for downloading online, but most of the important parts are covered here.
But isn't that Shannon who introduced the idea for block ciphers, the diffusion and confusion parts?
I think so, yes. He was, yeah, Claude Shannon.
Okay.
Yes, he was quite prolific in the information theory and in the coding and ciphering and cryptography. Yeah, he was quite all over in his time. This concept this actually held, and everyone is using what he thought about. Now we will focus on just a small sub part of where we can measure information at, namely in the context of discrete random variables, in the context of sets which are finite or countable at most, and we will see how we can measure the uncertainty or a measure of chaos in such systems. Now, suppose we have a random variable which can have values x1, x2, x3, x4, and so on and so on. And the set of the possible values will be denoted as curly x. Now the probabilities of the individual values will be denoted as just p of x. We will mean by this the probability that the random variable will be equal to x. If there is no confusion among it, if it would be possible to confuse with something else, we would just use the lengthened notation. Now, for the probability distribution on this subset, we will just use the small letter p, meaning just the set or vector of probabilities. Okay, px concerning the probabilities on the set of possible values of variable x, qi denoting the set, the probabilities of distribution q over the possible values of variable y, and so on and so on. So that's just a shorthand notation, because we wouldn't like to waste that much space by just writing the lengthened full notation probability that random variable is equal to x. And now the definition of entropy, which is one of the concepts which is quite good to remember, is, that the entropy denoted as capital H of a random variable is minus the sum over all its possible values, probability of a value times the logarithm of the probability of the value. So entropy of a discrete variable h of x is just minus sum over possible values of x, probability times the logarithm of probability. Now, why it is minus a sum, why there is a logarithm, and what kind of logarithm it is, we will get to. Now, as I said, we will use the entropy to be measuring the number of questions needed to get information in a very rough sense. And because we are in the field of computer science, the number of questions, we mean the number of binary questions, yes and no question, 0, 1 questions. So we will be working with logarithms with the base of 2. Okay, so if we don't say otherwise, we mean logarithms with base 2. Then we call it the binary entropy, for example. At some points, we need the logarithm with a different base. In the entropy settings, this is always stated. Most of the time, people are just working with ones and zeros. Now, if we have a value which has a 0 probability, inserting 0 in a logarithm would put us into minus infinity. Well, in a limit approach, but in a limit approach, 0 times logarithm 0 is 0, because a polynomial always wins when competing with a logarithm. So for probabilities being 0, we just redefine p times log p to be 0. If you take a look at the definition, it doesn't actually matter what are the values of the random variable. Yeah, here we have the probability of x1, probability of x2, probability of x3, probability of x4. But at no point here in the formula we have what are the actual values. The values can be 1, 2, 3, 4. The values can be 10, 100, 124, and 42. Doesn't matter. The entropy is still the same. It only takes as its input the actual probabilities of those values. Okay. If we will be then later on talking about messages and encoding, we would be actually having random variables with values A, B, C, D, E, F, G, and so on and so on. What we will be aiming to do in the long run, and what we will try to do in your homeworks, is to establish an efficient binary encoding of a text. If you have an English text, which letters, well, from the English alphabet, and you would like to encode this text into ones and zeros, basically what you can do is think about which letters encode in which way, which of them should have longer codes, which of them should have shorter codes, and this is what the entropy will be actually useful for. So it doesn't matter what are the probabilities of the individual, what are the individual values, they can be A, B, C, D. It matters what are their probabilities. When talking about texts, the probabilities would be the relative occurrences of letters in a random English text. And we will be aiming to, well, how to establish an efficient encoding for such a case. Now, as I said, we will use the basis of 2 in the logarithm, and this basis actually measures the units of the entropy. If we have the base of 2, then the entropy is given in bits. And it actually gives us, roughly speaking, what's the expected number of yes and no questions needed to get an answer to what of the letters, what of the values is actually happening. Okay? Very roughly speaking. At some points, people might want to work with a decadic entropy, or, well, just the digital representation. At some points, people want to work with natural logarithms, with units of nats, and by what we know about logarithms, converting an entropy with logarithm of one base to another just means multiplying the whole entropy by a constant of the logarithm corresponding to the change of bases. So it's not hard to switch between entropies with different bases. Yeah, if we have an entropy with one base, then finding the entropy with a logarithm with other base just means scaling it by a factor. That's not that hard, but most of the time we'll be just working with binary entropy. Now, where does this definition come from? Now, you recall the expectation of a random variable is, if it's discrete, sum over all values x times the probability. In this case, let's just use the shorthand notation px. Okay, that's the expectation of a random variable. If you apply a function to the random variable, then the expectation of a function is just sum g of x times probability. And if you take a look at the entropy, then you will see that the entropy is just sum and now minus logarithm of the probability times the probability. So it is the expectation, the expectation of minus logarithm of probability. So expectation of minus logarithm of probability. And this minus logarithm of probability of a value is called the information value. Of values.
So, but where's the px coming from?
The
The
px
second px.
is basically probability that the random variable is equal to x.
Yeah, but there's log of px.
Yeah, that's coming from here.
Okay, fine.
That's like the logarithm applied to the probability, right? The information value. And now, why is the information value interesting? Why it is the minus logarithm of the probability? Now, let's take a look. The probability is always between 0 and 1, right? The logarithm of something, that's a function looking like this, right? Here is 0, here it's 1. Now, if we take minus logarithm, we get the function which is just flipped. And if we insert probabilities in the logarithm, here minus logarithm of a probability, then probability is always between minus 1 and 1. Between 0 and 1. So we'll get values between here and there. So the results will be between here and there. Okay. So if we insert here a probability which is large, the information value is small. That's the measure of uncertainty, measure of surprise. So the more sure the value of the random variable is to happen. So the closer the probability it is to be equal to 1, the less will it surprise you when it actually happens. Okay. So if you insert something large here, close to 1, this thing will be close to 0. The less probable a value is, so the smaller this probability is, the larger is the information value, the measure of uncertainty in that. Okay. So that's why the logarithm is used, the minus logarithm is used as, or the probability is used as a measure of uncertainty. Yeah, if you have a system when there are two values possible, one of them is highly likely, say 0.9%, so 0.9, 90%, and the other one is quite unlikely, 10% or 5 or 1 or whatever, then it is much more surprising if a smaller one comes up. So it has larger information value in it. And the entropy is the expected information value. So it takes all possible values which can come up and multiply the measure of uncertainty in them by their actual probability of occurring and weights them up. Okay? And this gives you an idea how much uncertainty is hidden in the system, how much unsureness. Okay. Now, the entropy could also be introduced axiomatically, and we would get the same definition. Yeah, in the way that it is always non-negative. It is 0 for events which are sure. The less likely events are, the more likely, the larger uncertainty they have. And if we have independent events, so knowledge of one of them does not give you any information about the other, then their uncertainty is added together. Now, looking at it from the perspective of events, if A and B are independent, then the probability of A and B is the product of probabilities, right? And what happens if you apply a logarithm on a product?
It's a sum.
It's a sum. So that's the motivation behind using logarithms here. The information among events or values which are depending on each other is overlapping. And if they are, on the other hand, independent, and knowing something about one does not give you information about the other, then the information, the uncertainty hidden in those independent events, independent variables, let's say, is added together. Okay? Now this is all waving hands around by giving you a motivation why the definition is given exactly in this way. We will then see on exercises how it actually works and how it ties into the information theory. Now, first thing which we need to know is that the entropy is always non-negative. Now, proving this is quite easy. You take a look at the definition, and we have minus some probability times the logarithm of probability. Now you know that the logarithm is always negative for its argument between 0 and 1, right? So if you take this minus, put it in front of the logarithm, you get something which is positive or 0, but never negative. You multiply it by a probability, which is also never negative, only positive or 0, and then you'll take a sum. So you are taking a sum of products of things which are either 0 or positive, so you never get anything which is negative, right? Now, that's quite easy. Now, let's take a look. What would be the entropy hidden in a system which has only two possible values? So let's suppose we have a random variable, have values 0, 1. Both equally likely. And we want to find its binary entropy. Okay, let's take a look. The binary entropy is minus some probability times the logarithm of probability. Okay, so if we have only two values, so that's just the sum over, well, that's just one thing plus the other. And if they are equally likely, what are the probabilities? 1/2 and 1/2, right? So this is just minus 1/2 logarithm of 1/2 minus 1/2 logarithm 1/2. Good. And what is the binary logarithm of 1/2?
-1.
That's -1, right? That's like minus the logarithm of 2. Yeah, we just flip those. And logarithm of 2 is 1, so -1. So what we get is minus 1/2 times -1, minus 1/2 times -1, so basically 1/2 plus 1/2, which is 1. So, in such a system, where there are only two possible values, 0 and 1, and they are equally likely, the entropy of this system is 1 bit. This tells you that you need one question to determine the result, on average. Okay. Now, what if the probability of 1 is, let's say, some general small p, and probability of 0 is, let's say, 1 minus p. Then the entropy is minus, well, p logarithm of p minus 1 minus p logarithm 1 minus p. Which, for given p's, is a function looking like this. So, if p is equal to 0, which means that the random variable is actually not random, and it is always equal to 0, there is no uncertainty in the system. You always know what the value will be. The same if p is 1. Okay, if you know that the random variable is equal to the value, you don't have to ask. Okay, if p is somewhere in between, the interpretation is not that straightforward. Expected number of questions in this case does not apply directly, because we cannot ask like half a question, right? But the entropy interpreted as the measure of uncertainty is then larger and larger the closer we are to a uniform distribution, 0 and 1 being equally likely. Okay? We will see this next time, that this can be generalized for distributions which have not two, but multiple possible values. If they are all equally likely, the entropy is largest because there is the most chaos in the system. If one of the values has 100% of happening and the others cannot happen, then the entropy is 0 because there is no uncertainty involved. Okay?
Yes.
Good. Are there any questions to that? Okay, so we'll continue with the entropy on Wednesday. So, see you then.